topics. One is on total internal reflection conditions, and another one is on reflection through the prism and optical instruments. So these are the things we'll be discussing today. So coming to the first topic of us, that is your total internal reflection. So whenever the light ray passes from a denser medium to a rarer medium, so this is your optically denser medium to a rarer medium. So with respect to a normal, when it is being allowed to pass from the light ray, so this is your this is your angle of incidence ray, making an angle of incidence I. So at a particular angle of incidence. So generally what will happen, the light ray is passing from a denser medium to a rarer medium, it bends away from the normal like this. At a particular angle of incidence, which is called as your critical angle C, the light ray graces through the surface between separating the both the mediums in this way. That means at an angle of incidence where I is equal to C, called as a critical angle, your angle of refraction, that is R, will be equal to the 90 degrees. Okay, so this is the condition, sir. At this particular instance, it will be the angle of incidence will be greater than 90 degrees. Or if the angle of incidence is greater than the critical angle, then the light ray reflects back into the same medium, and this phenomenon we call it as an TIR, as you know this particular thing. So in this particular case, the angle of incidence should be greater than or equal to just critical angle condition. In this case, the refractive index of the denser medium into the sine angle, that is C, is equal to mu refractive index of the rarer medium into sine angle of refraction. Here the R is equal to 90 degrees. In that sense, mu is equal to, or suppose if I take the rarer medium as an air whose refractive index is equal to 1, then mu can be written as an sine 90 by, that is sine C, or which is equal to the 1 by sine C. So for the TIR to take place, this has to be greater than, the refractive index has to be the greater than that particular, in this case, critical angle. That is, angle of incidence has to be the greater than critical angle. Okay, so these are the main conditions. Uh, okay, so that means sine C should be, or else your sine C should be greater than, this is 1 by mu. Then we can get this particular relationships. Fine. So that means the light ray is going to be reflected back into the same medium. This phenomenon we call it as a critical total internal reflection, and this is a phenomenon that will be used or discussed in a communication systems or in a medical purposes or in a different cases, decorative cases, etc. So majorly in the optical fibers, the same phenomenon is going to be used. If I consider, or if we consider any optical fiber, it consists of a two layers like this. So the layers which are going to be inner layer is called as, and this is called as a core, and this layer is called as a cladding. Refractive index of the core, refractive index of the core will be greater than the refractive index of the cladding. That means, so whenever the light ray enters into this optical fiber, that means it is trying to move from a denser medium to the rarer medium. Due to that, the core is going to be greater than the cladding. So when the light ray is being incidented at an angle called as a theta L, called as a launching angle, the light ray reflects back over here and it hits the surface of the core. From there, it undergoes the total internal reflection, and in this way, the light ray is going to be hitting at every point. Wherever it touches the surface, it undergoes the total internal reflection. Thus, the light ray will be propagating in the medium. So at this particular angle, it is called as an C. This angle will be 90. This will be your 90 minus C. This angle will be. So when you solve this one, that is mu is equal to, that is, or your sine C over there can be written as a refractive index of the cladding by the refractive index of the core. Okay, so now this one you can use it, or from this one you can find the C value is going to be how much. If I apply the Snell's law for the launching angle and the 90 minus C, then it will be the refractive, the launching angle is in the air, so that is mu is equal to, it will be the sine theta L by, this is going to be the sine of 90 minus C. So which is called as cos C, or your launching angle or sine of theta C is equal to the refractive index of the core into cos C. We have got the sine C. If you can substitute the cos C here, you can find what is your launching angle is there, and that is nothing but an theta L is equal to sine inverse of, this is under root of refractive index of the core square minus the refractive index of the cladding square. So that means if we send a light ray with this particular angle called as an launching angle, the light ray which is entering into the optical fiber cable will undergo the total interreflection, and the light ray can be transmitted from one point to the another point without any loss of or less loss of energy. So coming to here, as we have discussed it, the total internal reflection when the angle of incidence is equal to the critical angle. That is theta I angle of incidence is equal to critical angle. He is asking what will be the angle of refraction. What is the angle of refraction will be, sir? 90 degrees. Just now we have seen. At the critical angle, the light ray graces through the surfaces of the denser and the rarer medium. So this is your angle of, this is your 90 degrees. Okay. So next one, please. So now what's going to be under the total internal reflection conditions? So under this total internal reflection cases, suppose if we take a prism and this is your normal to the light incidenting here. So this is your angle of incidence. I am taking it as an I1. Now here it might be reflecting, refracting in this case. This is your R1, and the light ray is going to be emerging out. So this is your I2. This will be your R2. And this is your angle of prism A. So now according to the rules of the prism on this case, that means you can write it as an R1 plus R2 is equal to angle of the prism. R1 plus R2 should be equal to your angle of prism over there. And I1 plus I2 is equal to angle of the prism plus deviation. So these are your basic rules or basic laws for this particular case. So if in this case the total internal reflection has to happen, instead of the light ray going outside, it has to come back in this way to undergo the total internal reflection. So for the light ray to come back in this way like this R2 should be your, the value of the R2 has to be your critical angle, that is R2 should be equal to the C. So if R2 is equal to C there, okay, so this happens this when only the, that is the, then R1, this can happen only if the, for example, the I1 has to be the 90 degrees and R1 should also be your critical angle. So if R1 and both of them are going to be the same, that is 2C is equal to A, that is critical angle C is equal to A by 2, or this is the condition where light ray will be graces through the surface here. So that means the light ray, whatever is there, it's going to be grazing through this light. So if in this first case, in this situation, then your angular, that is I2 value will be equal to the 90 degrees, or angle of emergence is equal to 90 degrees, or anything in this situation, your I1 value is equal to 90 degrees. This is your first case, or else if C greater than the A by 2, on the sense 2C is going to be greater than the A, or If the angle of the prism is less than the 2c, then the total internal reflection takes place. Then the TIR takes place. That means light ray which does not emerge out of the prism. This is the condition for the no emergence. When the light ray will not emerge outside, please. It will come back into the same medium. So this is the condition for your total internal reflection to happen inside the prism. Or else in this third case, if C is going to be the less than A by 2, or your 2C is less than A, or if the angle of the prism is greater than the 2C, then the normal thing, that is normal emergence light ray, will be coming out of the prism, or emergent ray will come out. Emergent ray exists. So this is the condition for the no emergence situation, that is a total internal reflection in the prism. So now if we see this particular question, a ray of light incident normally on the isosceles. That means here the angle is 90 degrees. For the angle of incidence I is equal to 90 degrees, angle of refraction will also be 90 degrees here, normal refraction. So if this angle is going to be 90 degrees, it's an isosceles. Here the angle is going to be 90, means the angle at the A will be and equal to the angle at the B. Both of them will be 45 degrees. Since the angle at the A is 45 degrees, this is 90 degrees, and here it is a normal. Let me take this as a point D. Then this angle is also, sir, 45 degrees. So due to that, the light ray has been traveling here, and your critical angle C will also be 45 degrees. This is your C and this is your C, both of them. So since critical angle is value we have got, it's at 45 degrees, then according to our conditions, then the 45 degrees, or that is your 45 degrees, is going to be greater than the C for the total internal reflection to take place. In the sense, if I apply the sign on both sides, sine 45 greater than sine C, or else 1 by root 2 greater than whatever is going to be the sine C is nothing but the 1 by mu, or you can say that mu value is going to be greater than the root 2, or at least possible value in this is greater than or equal to the root 2. So this is the condition for the case, sir. Next one, refraction through the prism. So let us derive the refraction through the prism. If I consider this as one of the prism, okay, it's a prism whose apex angle or the refracting angle or the angle of the prism is going to be the A. Suppose this is the corner vertex A name, and simultaneously this is BC. Angle of the prism is also A. Generally, it is represented by this particular one. Okay, now this is the your equilateral triangle. Let this be your primary normal or the first normal. Let me take it as an N1. And light ray is incidenting to the normal with an angle of I1. So it is going to be, this is the normal I'm extending here. This is the light ray which has been passing through the prism. Okay, so from here, the light ray is emerging out of this particular thing. And this will be your angle of emergence. This is I2 with respect to the normal here. This is N2. So while entering, the light ray is coming from a rarer to the denser medium. So this will be your refracting angle R1, and this is your refracting angle R2. While leaving out the prism, it is moving from a denser medium to the rarer medium. So this is the actual path of the light ray needs to be traveled, but this is the path it has emerged out. So this angle is called as an angle of deviation. So this particular angles, this you can write it as an, I'm writing here, which is I1 minus R1, and this particular angle I'm writing here I2 minus R2, and this is your angle we need to identify. Let's name them. This is A, this is P, this is Q, this is your R, and this is S. And I'm writing here angle S is equal to 180 minus angle of deviation. 180 minus angle of deviation, that is your delta. So now taking into consideration first one, if I go for the triangle, this is PQR. So from this triangle, we can write it as an R1 plus R2 plus angle Q is equal to, that will be the 180 degrees. So this is the first equation, and from the triangle, another triangle, it is PSR. I can write it as an I1 minus R1 plus I2 minus R2. Another one is an angle S, which is equal to the plus 180 minus angle Q is equal to, oh sorry, 180 minus delta here. 180 minus delta, this is the angle over there. Okay, is equal to how much? This will be the 180 degrees, cancel them. So from this one, I can say that I1 plus I2 is equal to R1 plus R2 plus delta. This is your second equation, first and second. And from the quadrilateral, that is from APQR, you can say that angle of the prism plus 90 degrees plus angle Q plus 90 degrees is equal to 360, or else A plus angle Q is equal to 180, or angle Q is equal to 180 minus A. Now when you put down in the relationship over there, in the first equation, angle Q is equal to 180 minus A. You will be getting your first important relationship for the refraction through the prism. R1 plus R2 is equal to A, and your I1 plus I2 will be equal to the A plus angle of deviation. These are the important two equations, and when you solve, you will be getting the refractive index equation as an sine of A plus angle of minimum deviation by 2 by, this is sine of A by 2. So at the minimum deviation, what will happen? At deviation minimum, your I1 will be equal to the angle of incidence is equal to angle of emergence. So R2 is equal to R1. So these are your conditions, and this is the minimum deviation situation where the deviation between or angle between the incident ray and refracted ray, both of them will be minimum. Now, when you try to solve this one, the angle of incidence of the ray is going to be 45 degrees. That means I1 he has given it as an 45 degrees, and the angle of the prism A is equal to 60 degrees. So this information is given. If the suffers the minimum deviation, he is mentioning specifically at the minimum deviation. So it's a sine function. So if we plot a graph between the angle of incidence and the um, deviation and the angle of incidence, the shape of the graph will be like this, and this will be the value of the minimum deviation, where you will be getting the values of the I1 is equal to I2. Both of them will be the same. So suppose this one, the minimum deviation is asking what is the minimum deviation and refractive index. Since it is a minimum deviation conditions, I2 or I1 and I2 both should be equal to the 45 degrees. Angle of the prism we do have. So from the relation, I1 plus I2 is equal to A plus angle of the minimum deviation. So this is 45 plus 45 is equal to angle of the prism is 60 degrees, and this is your minimum. So your minimum deviation will be equal to the 30 degrees. That means our answer should be either the B or D. Now we'll go for that. Refractive index, substitute in the refractive index formula, which is sine of angle of the prism plus minimum deviation by 2 by sine of A by 2. So in that sense, then it will be the sine of 90 by 2, which will be 45, This is sine of 60 by 2, that is equal to the 30. Sine 45 is 1 by root 2, sine 30 is 1 by 2. That means you should be getting your angle of the refractive index as root 2. So now coming to our next part of the array of this one is an optical instrument. So first one is our simple microscope. A simple microscope consisting of a one converging lens, a single converging lens will be using, where you are going to place the object between the focus and optic center of the lens. This will be your U. You are going to place the object between the focus and optic center. Because of this, the light ray, whatever is going to be there, that will be an erect, magnified, and erect image is being formed, magnified image is formed, and that falls behind your object distance. This is the object, and this will be your image location, where this is called as an V, and this is your focus F. Then I'm solving this one for a simple microscope. So the light rays actually will be traveling like this. The real rays they not meet, and the virtual thing will be there. On solving this one, you'll be getting your magnification formula as m is equal to 1 plus d by f, where d is called as an least distance of distinct vision. Distance of distinct vision. That means it is the minimum distance where the human eye can see an image clearly is 25 centimeters. So this is your least distance of distinct vision conditions, please. Okay, so this is a simple microscope where the object will be placed. These points are also very, very, very important in this particular case, where the object will be placed within the focus and optic center here, and image will be falling behind the lens, behind the object, where the type of the image is going to be the erect and erect image, and it's a magnified image, okay, and it's a virtual image, and it's going to be falling at a least distance of distinct division. Here V is equal to the D, and the value of the D is going to be 25 centimeters. Value of the D will be equal to the 25 centimeters. It is for the normal human eye, it's a standard value where you need to remember this particular value. So this is the formula for the magnification of a simple microscope, which is m is equal to 1 plus d by f, where the image is going to be falling at the least distance of distinct vision. In the same simple microscope, if you want the image should be falling at the infinity, then you need to place the object exactly at the focus of the this converging lens. If I place the object exactly at the focus, as we know, if an object is placed at the focus, then its final image is going to be false at infinity, where the two parallel rays will be emerging from here. So this is one parallel ray, this will be the another parallel ray. These two rays can never meet either on the real side or on the virtual side, please. So these are your conditions. Okay, so when you want to have the image at the infinity, that we have to place the u value exactly at the focus. We have to place the u is equal to, this is focus of this particular lens or converging lens that we are using. So please remember these things. So the second one will be going for a compound microscope. Compound microscope. So compound microscope consists of two types of the two lenses. So what are they basically? One is called as an objective, another one is called as an eyepiece. So two lenses will be there in this case. One is called as an objective, another one is will be an eyepiece. So in this case, the objective is going to be the smaller one, and the eyepiece is going to be the larger one in the from which we observe the things, and the distance between them is called represented by the L here. So now for the general usage, we'll be placing the object between the focus of the objective and center of curvature of the objective. So the image falls behind the two f0 here. First image I1, that will be an inverted magnified image. So when this image is being taken as an object for the eyepiece within this one, then your final image will be falling over here. That will be an final image I will be falling behind the C here. So if you want, you can just put down the ray diagram over here like this. The rays will be passing and your final image. The eyepiece is going to be just behaving as an your simple microscope. Then the in this case, this is called as an near point method where the image falls at the least distance of distinct vision, that is 25 centimeters. In this case, the formula of the magnification can be written as an this is minus V naught by U naught into 1 plus D by Fe, and your distance between the microscope can be written as an V naught plus UE. So this is going to be the V naught and this will be your UE. So in the second method, which is called as an far point or normal adjustment method, it is called as an normal adjustment method where your final image V will be falling at the infinity. For this case, you can have your magnification formula as M is equal to minus V naught by Fe, because you are going to place the object at sorry you are going to place the your final image at the infinity conditions. So to have the image at the infinity, we have to place the object at the focus. So since for that reason it is V naught by U naught into simply D by Fe. Since this is 1 by V value will become 0, and your distance between the two lenses will be equal to the V naught plus Fe, since UE is being converted as an Fe. So in this relationship for the case, for the time being, you can write that if at all, if your U naught is going to be approaching towards the F naught, then your V naught will be approaching towards almost equal to the L. In that situation, your formula can be written as an instead of the M is equal to V naught, you will be writing it as an L by F naught into 1 plus this smallest changes we have to do according to the information that he is going to provide in the question, please. Okay, so now coming to the astronomical telescope, remember these points, theoretical points also they might be asking, where do we place the object? We'll be placing the object between the center of curvature and focus of the objective. So these points should be very, very important. Remember, theoretically, they might be asking you these type of the questions also. At every point of the construction, they can ask you a question. Another one is an astronomical telescope. A telescope is the one which is used basically to see the distant objects. So that means your basic object will be generally at the infinite distance or the long distance. For that reason, your objective will be a bigger one and your eyepiece will be a smaller one. So this is your f naught focus of this one, this will be your Fe. So general formula of the magnification is equal to minus f naught by Fe. Here negative sign indicates for an inverted image, please. Or else for the near point, this is for the far point. That is your final image will also fall at infinity. For the near point conditions, you can write it as a minus f naught of 1 plus the or 1 by d plus 1 by Fe. So like this is the near case, you can use this particular relation astronomical telescope. So coming to the question on this one, astronomical telescope. An astronomical telescope has an objective of the focal length, as I have told you. Objective will be bigger one and eyepiece will be a smaller one. To view an object which is 200 centimeters away, that means the object is at the near place. It's not away far away. The lenses must be separated. He is asking what is the L is going to be how much. So primarily he has given F naught is equal to 40 centimeters, Fe is equal to 4 centimeters, and the U naught is equal to the 200 centimeters. So this is the information he has just given to us. Okay. So based upon this particular information, what we need to solve. So if I take further, that means you are having the lenses like this. So first is an objective. So before the objective, there is an object which is at a distance of 200 centimeters. This is O. So for that one, I am going for a lens formula, normal thing, that is 1 by V naught minus 1 by U naught is equal to 1 by F naught, or else substitute the values. I don't know where it's going to be the image, but object is at a distance of this is minus 200, since the object is on this the side of the light, emerging side. Why you are calculating all these things? This is 1 by 40, because you need to calculate the L. To get the L value, two values we need. 1 by V naught we need. Another one is going to be the Fe. So I'm trying to get the V naught. So because your final image is going to be falling at the infinite conditions. So on that sense, when solve this one, you'll be getting it as an that is 1 by V naught is equal to 1 by 40 minus 1 by 200. Okay, so this should be the 5 minus this one, that's going to be the 4 by 200, or this will be the 1 by 50, or your V naught is equal to 50 centimeters. So that means your L is equal to V naught plus Fe, in the sense 50 plus 4, which is equal to the 54 centimeters. Where is there? It is okay, it is in the option D. So this is what the separation between the two lenses is. Next one, if we go for the compound microscope, okay, a compound microscope which is used to enlarge the objects, please, is used to enlarge the object kept at a distance of 0.03 meters, okay, as given in terms of the meters. That means he has given it as an U naught is equal to 0.03 meters. So I'm also maintaining the same thing. So now, from the objective, which consists of the several convex lenses in contact and has a focal length of, that is f naught of this one, focal length is equal to 0.02 meters. So focal length is if a lens of focal length is 0.1 is removed. So he is having a group of lenses. He's having a combination of the lenses. He's not having the one lens as we have discussed theoretically. So objective is having it's a several lenses, group of lenses are in contact, and the combined focal length of all the lenses is 0.02. So out of that one, he is removing one lens whose f1 I call it as a 0.1 meter is been removed from the objective group. Then by what distance the eyepiece of the microscope should be moved to refocus the image. Okay, so where is the actually the first image is going to be falling for these values, sir? So for that one, I'm going V naught minus 1 by V naught is equal to 1 by U naught is equal to 1 by F naught. So since we don't know the value where the final image, 1 by V naught is equal to minus of this is 1 by minus of 0.03, and your combined focal length is 1 by 0.02. So when we solve them, V is equal to V naught is equal to, you should be getting it as a this denominator or numerator will be 0.02 into 0.03 by difference between these two things, that is going to be the minus 0.01. So obviously you will be getting it as an 0.06 with a negative sign, that is image is also falling on the same side. From this case now, If I want to now have the final value of removing the focus. So if I remove the f1, what is the focus of the remaining lenses? That is 1 by f naught minus 1 by f1, which can be written as an 1 by 0.02 minus 1 by 0.1. That means your f dash can be written as an 0.1 by 4, or this is equal to 0.025 meters, or you have to shift by 25 centimeters in this case, please. Okay, so now this is your condition. Fine. So now there are some other examples, we can solve them. This is your first in case. A beam of light is there of red, green, blue colors are there. Fine. On the right angle prism, that means here 90 degrees means here 45 he has also given. So this angle should also be the 45. The refractive index of the material of the prism for the red, green, and the blue. This is refractive index of the red. This is refractive index of the green. This is refractive index of the blue. The prism will, what it's going to be doing. So let us first find out the refractive index of the prism here, or the critical angle. So when the light ray is falling normally on the surface, it hits the EAC surface where it will be undergoing the total internal reflection. This is your critical angle. So on solving, what you will be getting, critical angle will be equal to the 45 degrees, sir. That means your angle of incidence should be greater than the C value. So that is your angle of incidence over there is 45 degrees. From this one, refractive index mu is equal to sin I by sin r, in the sense r value is going to be 90. If I take that one, that is sin 45 degrees should be greater than 1 by mu, or from this one, mu should be greater than root 2, and your root 2 value is 1.414. So now in this situation, when we compare, the refractive index of the red is less than the refractive index of the prism. Okay, so that means the red will pass through here. So in the refractive index of the green is equal to the refractive index of the prism. The refractive index of the violet is greater than the refractive index of the prism. That means your green and blue lights will uh, they will undergo the will be TIR. They will undergo total internal reflection. Okay. So next one, the magnifying power of an astronomical telescope M he has provided, sir. The magnifying power of an astronomical telescope is going to be the 10, and your length of the telescope is equal to 110 centimeters. So for the normal adjustments, that means final image falls at is at infinite. So final image is at infinity means then what are the value formulas? L is equal to, that will be the F naught plus Fe, and magnification formula will be the F naught by Fe. So I'm not going for an okay negative value in this sense, or if you want you can go for the negative value also. Now the F naught by F, from solving this one, F naught by Fe is equal to 10. From this one, F naught is equal to 10 Fe. Substituting in this relation, L is equal to, that is 110 is equal to 11 Fe. From this one, Fe is equal to 10. Since Fe is equal to 10, F naught is equal to 10 times of Fe, which is equal to the 100. So now we have got the F naught and Fe values. Now he is asking the magnifying power least distance of distinct vision. So what is the formula for the magnification formula for the astronomical telescope for the least distance of distinct vision, sir? So here I have written, this is for a near point. Okay, so now substitute that relationship here. So magnification is equal to, so I can write it as an minus f naught of 1 by d plus 1 by fe. From this one, f naught is going to be the minus 100, replace them 1 by d. What do you mean by 1 by d? That is 25 centimeters standard value, least distance of distinct division. Fe value is going to be coming out to be how much, sir? 10. So when you solve this one, you will be getting obviously, so that is minus 100 of, so what's going to be your LCM, sir? 50 in the sense 2 plus 5, so which is going to be the 7 by 50. If I cancel this one two times, then it will be the minus 40. Okay, this is your magnification of the, where for the least distance of distinct division, that is for a near point method. Great. So this is your one of the situation, please. Next one. The magnifying power of a telescope is 9. When it is adjusted for parallel rays, the distance between the objective and eyepiece, that means L is equal to 20 and magnification M is equal to 9. Focal length of the lens is asking. In which case, adjusted for the parallel rays means the rays which are been falling on this one should be parallel like this, and these rays will never converge like this. They cannot converge in this situation. In that sense, it is a final image is falling at infinity. So that means you can write it is f naught plus fe, and it is equal to the 9, and magnification m is equal to f naught by f e with a negative sign. Obviously, that will be there. So what is your magnification? Sorry, magnification is 9 and distance between them is 20 centimeters. So from this one I can write the f naught is equal to 9 fe. Replace here f naught plus fe in the case, which is going to be the 10 fe is equal to 20. Fe is equal to how much, sir? 2 by 1, or which is 2. This. So if fe is equal to 2, then what will be the f naught, sir? F naught plus 2 is equal to 20. That means F naught is equal to 18 centimeters. Okay. So this is how, this is the one. Next one, sir. For a prism of refractive index 1.732, that means can I express the 1.732 as root 3? We can be using in the different if it is necessary. The angle of the minimum deviation is equal to, that is delta minimum is equal to the angle of the prism. These two are same. Then he is asking what is the value of the A. What is the formula, sir? Mu is equal to sine I by, or else sine of A plus, this is dm minimum deviation by 2 by, this is sine of A by 2. Now root 3 value, root 3 is equal to, and your angle of the prism and angle of deviation delta m, both of them are the same. That means sine of, can I write it as a 2a by 2 by sine of a by 2. So root 3 is equal to sine a means denominator it is a by 2 is there, and numerator it is the sine a is there. That means it can be written as an 2 sine of a by 2 into cos of a by 2 by sine of a by 2. These two will be removed here. So from this one, root 3 by 2 is equal to cos of a by 2. What is cos a by 2 value is? Root 3 by 2. In the sense, how much this should be your, sir? 60. The angle of the prism he is asking. So that means it cos 30 degrees. This is cos of 30 degrees in the sense pi by 6. So that means your a by 2 is equal to how much, sir? 30 degrees means angle of the prism should be 60 degrees. So this is the situation, sir. Next one. A prism having an apex angle of 4, and the angle of the prism is 4 degrees. The refractive index is 1.5, is located in front of the vertical plane mirror. So actually this should be the case. There will be a very thin mirror. Angle theta is equal to 4 degrees. So 4 degrees, there is a mirror over here. The light ray that we sent over here, it will be reflection, undergoing the refraction and hitting the surface and coming back like this. So now these are the different angles. For the small angled prisms, deviation is equal to A into this is mu minus 1. From this one, angle of the prism is 4 into 1.5 minus 1. Okay, so on solving this one, what you should be getting, sir? You should be getting it as in 2 degrees. So 2 degrees, but once you have got the 2 degrees, then it will be reflected and refracted. So then the angle of the reflection will be, then the angle of reflection, angle of the reflection is equal to 176 plus 2, which is equal to the 180 degrees. Sorry, it's 172, 178 degrees. So this should be, because it is actually, it has to go like this. It might be written. So this angle, this is going to be the 4 degrees. Okay, so this is what he is asking, which is 178 degrees. So this completes our today's session of the physics class.